construction issues, because otherwise I might get carried away and not get to the others. So as far as the threading system is concerned, here's my first controversial statement. A number of Java virtual machines, at least in the past, have implemented their own thread implementations. I think this started with the Sun Classic VM. I think Jike's RVM still does that. I think Natural Bridge still does that. To the extent that it's still there, yeah. My feeling here is doing this sort of based on experience many years ago is that getting interoperability right in this case is tricky. It's probably possible if you're clever enough to implement your thread system, make sure that that native code sees the right kind of environment. It's probably not completely impossible, but it's very difficult to get this right, particularly if your so-called native code actually knows about threads itself and forks threads in order to just do some of its work faster. The reasons for implementing your own thread system as part of a virtual machine typically include things like you get better performance that way, or otherwise you can't support sufficiently many threads as are required by the Java or whatever application. I actually believe at this point that the justification for that is mostly going away. In general, this was true to some extent because some of the older platform thread libraries were in fact implemented rather poorly, sometimes for fairly superficial reasons. So there were bad performance results. There were real bad performance results with some of those vendor-provided thread libraries. On the other hand, thread libraries are getting better, and some of those comparisons I think were not particularly fair anyway. People have a tendency to overlook that the platform thread libraries actually do some clever things which are actually worthwhile in places. So, for example, platform thread libraries tend to worry about processor affinity a lot. Typically, sort of quick and dirty thread libraries, as people tend to build at the user level, don't. Which means that for toy examples, they run a lot faster. For real examples, things are much less clear. As a result, I actually expect that this difference is gradually disappearing.
Since you said this is controversial, there were two possibilities I think that run throughout your talk. One is the JVM or whatever can learn to accommodate the APIs that the OS provides, or it could be that you go the other way around. So one of the things that an OS can provide is an ability for a language system to implement its own threading package more easily. And so, for example, K42 does that.
Okay.
Which is an experimental Linux core.
Okay, we should probably discuss this offline. I'm concerned about some things there because, in general, one of the problems you run into is whenever you block on a particular lock, I mean, you basically end up in a situation where you end up with mixed kinds of threads. And blocking on locks.
The question is, when you block, what does the OS do? And does it tell the VM, the JVM or whatever, that it has blocked and ask it to do something else? If it does that, then
yeah, I mean, the problem is though you often want to maintain queues of waiting threads, right? And sort of all the players need to agree on how to do that. So I agree. If you can get them all to agree on that. That's another way of doing it.
The other issue is that for real-time systems, you tend to want to do very high-frequency context switching, and if you're using
right, I probably should have explicitly excluded real-time systems here because I mean my own feeling is more and more that at least hard real-time systems are really a different beast, and at least for multi-threaded programming, I've come more and more to the conclusion that you don't want to program them the same way as anything else.
So Hans, do you expect that platform threads would be aware of GC save points and switching contexts at GC save points?
Actually, I'll get to the GC issues.
Okay.
So. Hopefully. Okay, maybe I'll try to go through these quickly here. It's also fairly common to keep a thread pointed to, say, I think the Java thread structure, for example, in a reserved register. it's fairly important to have fast access to a thread pointer inside a JVM because you basically need access to the thread identifier in order to lock. On the other hand, I think the reason for this is getting much more tenuous. It used to be very slow on platform ABIs to get a hold of your thread identity, and that's actually improving. Most platform ABIs already have a pointer to a thread, which is good enough for locking, though it might not be the pointer to quite the right place. Unfortunately, on the most common architectures on both x86 and both the 32-bit version of x86, and eventually also on x86-64, unfortunately, if you believe that's where the world is going, that's also preserves this problem that it seems it's not completely trivial to get a hold of your thread pointer because it's only sort of in a register.
There's more information that you typically, if you hang up off of the thread pointer, you may hang caches for your heap. If you're playing stack balance game, you have to maintain.
Right,
stack
but in
balance.
fact, if you look at the native ABIs, you can there's a fairly standard convention these days for accessing thread local storage, which is simply a load off of something that you keep in a register. And that's even true for x86, x86-64. Actually, we'll get to that. Let me go to the next slide here. Allocation pointer in a register. That's somewhat important for allocation performance. At least that's the usual claim for doing it. It saves the thread local variable update per allocation, basically, at least, if you use bump the pointer allocation. You otherwise need to update a thread local variable for every allocation. But even if you look at what happens with the current ABI on something like x86, that's really, you can make the allocation pointer, I believe, be just one load away from a register, because it turns out the way the thread pointer is maintained on x86, that's still possible. It behaves like a register in this way, in this respect, but not for locking. So I think the overhead there is overhead, but it's relatively minor. So I mean, one comparison here, I said this was half-baked. I certainly don't have any measurements. But if we look at, if we compare the overhead to, for example, that of free list allocation instead of bump the pointer allocation, one would expect that the difference here is probably, waving my hands a lot, is probably no more. And I think that was estimated in a recent paper as less than 1% of total execution time. And I suspect in many examples, actually, even if you don't dedicate a register to the allocation pointer, you're going to end up caching it in many cases as well. So I don't think the difference there is actually all that much. And this is actually not a terribly important issue anyway, because even if you do decide to keep it in a register, saving it and restoring it on calls to native code is not a big deal. For calling interpreted code, there's actually a fairly clever trick that's used inside GCJ. I'm not sure how commonly that's used elsewhere. It's actually possible on most architectures, even fairly cheaply, to basically make an interpreted function look exactly like a compiled function. The details of how you do that are platform dependent, and GCJ does it using something called libffi, which is actually a nice piece of software that I don't think is very well known. But the basic idea is, if you look at some of the platform like Itanium in this case, I suspect Power is actually very similar. If a C function is represented as a pointer to a structure containing the code pointer, the instruction pointer, as the first element, and then a pointer to something that gives the context, the global offset table pointer, or some such thing as the second element of the structure. And basically, the second element of the structure needs to be loaded into a register before you branch to the first one. And that's necessary in order to be able to access global variables correctly. And on a machine like this, what you do, if you have a function that's really implemented via an interpreter rather than via native code, you instead represent it as something that looks more or less like the original structure, except there's some extra information at the end, like the pointer to the bytecodes. The code pointer that's encapsulated there is the pointer to the code for the interpreter. Instead of passing the pointer to the global offset table, you instead pass a pointer to the structure itself. And what happens is the interpretive, when it gets invoked, gets a funny value in its global offset table register.